Section 3.4, the derivative is a rate of change. So what we'll look at in this section is quite applicable stuff. If you've got a little exposure to physics, then probably you've seen some of these ideas before. So what we'll do is use derivatives to measure the rate of change in which some quantity, measured by the function f of x, changes as the input variable changes. This is useful in calculus, this is useful in physics applications, especially when we consider position as a function of time, in which case the rate of change of position is velocity, the rate of change of velocity is acceleration. We could speak now in terms of second derivatives. If we have a position function, the first derivative is velocity and the second derivative is acceleration, rates of change and rates of change of rates of change. So the benefit of this section is it makes to you some fairly physically tangible arguments that are still related to this fairly abstract calculus stuff. And we'll see some repetition of some of the ideas from the past, such as this one. Definition: the instantaneous rate of change of f with respect to x at x sub 0 is simply the derivative, f prime of x sub 0, which we could write as a limit of a difference quotient, assuming the limit exists. So instantaneous rates of change, they're derivatives. No news there. We've had exactly this kind of definition in the past. Well, we're interested in this section mostly in a particular idea where we've got this function f as a function of time t. If s equals f of t represents the location of an object lying along a coordinate axis. Okay, so t will play the role of time, s will play the role of position. Okay, in here we can't have two-dimensional positions, or three-dimensional positions for that matter. We'll be dealing with functions of a single variable that have a single output of the form s equals f of t, for example, y equals f of x. In calculus 3, you'll deal with vector valued functions, and then you'll be able to do these same kind of ideas in higher dimensions. And you're this close to doing it for vectors in here. And if you take a calculus class, physics class, it's calculus based, take a sophomore calculus based physics class, then you'll probably deal with vectors from the start. But for us in here, we got enough problems. We're dealing with what's called rectilinear motion. So we're dealing with a particle that it's located on a line and it moves left and right along a horizontal line, or it moves up and down along a vertical line as a function of time. So we'll have such a situation. We'll have position represented as a function of time. We'll take this point that's produced, this object to lie along a coordinate axis. We could take the coordinate axis to be a horizontal line or a vertical line. We'll do both. Vertical lines are more common applications. If I have then this object moving along a vertical line, I can talk about stuff like throw a rock up into the air. It goes up, it stops, it comes back down. So those are probably the most easily visualized types of movement that we'll deal with. So S is position as a function of time. The displacement of this object over the time from t to t plus delta t is defined to be delta s, which is a change in the function f of t plus delta t minus f of t. The average velocity then over that time interval delta t, the average velocity v sub av, v sub average, is the displacement divided by the travel time. It's the delta s divided by the delta t. It's the change in the function values over the change in the time values. We did that in section 2.1. We use this to inspire the study of limits, to find slopes of tangent lines and instantaneous rates of change. So this is overlapping with 2.1 a little bit. So average velocity, same thing we dealt with previously. We're not so interested in average velocity as we are instantaneous velocities and derivatives. If the coordinate axis is a horizontal line, we might have the displacement as given in the figure below. Okay, and what we have here then is an object moving, looks like a little arrow they put here. They indicate that the object is moving to the right, so it's moving in the positive direction. Displacement is positive since at time t we have the particle located here, the object located here. At time t plus delta t, delta time units later, the object is over here. So it has a net movement from the left to the right. It's moved in the positive direction. The displacement is positive, where we've defined the displacement to be the numerator and what we had above. The displacement is this quantity here, delta s, where the object ends up at time t plus delta t minus the position it had initially at time t. So it could move to the left or the right. That displacement could well be negative if the object was moving to the left. And it ended up to the left of where it started. Instantaneous velocity, we've practically dealt with this before, is the instantaneous rate of change of position. Velocity, or instantaneous velocity, is the derivative of position with respect to time. We totally set all this stuff up so that we could easily define velocity using derivatives. So if a body's position at time t is given by s equals f of t, then the body's velocity at time t as a function of time is v of t, the derivative of position with respect to time. Here it is written in terms of a limit. All right, we ain't so interested in these limit observations anymore because we're getting pretty good at taking derivatives and we don't have to go back to the limit definition. So a conversation purely in terms of derivatives would be something we're plenty mature enough to deal with at this stage. So derivative of position is velocity, is the shorthand of that observation. If instead of having the coordinate axis on which this particle moves to be horizontal, if we had it vertical, which is easier to visualize, I think, we might get something like this. So t, the time axis, is horizontal. The position, the location axis, is vertical. So we got two things going on. We've got time and we've got location. If you wanted to play this as a movie, what we would have is a particle moving up and down along a vertical axis. If I watched it as a movie, so I'm burying time in a sense, and not getting pictures in 2 dimensions, but getting a movement in one. And that's what we're describing. That's what we're modeling. If we have s equals f of t, and we have a coordinate axis vertical, then what that particle is going to do is it's going to move up this axis as time goes by, and it might move down this axis as time goes by. If it moves up this axis, then as time goes by, so that would be movement in this direction along the time axis, we would have a position would go up. And as time went by, we'd see the point in, I like to call it space-time. It's actually time-space. It's time on the horizontal axis and space on the vertical axis. But that's the right idea. As time goes by, position goes up. Time always travels in the positive direction. We'd see a graph for the function that would look something like this. The function would be increasing if, as time goes by, the particle moves upward. If, as time goes by, the particle moves downward, we'd see time moving forward, position decreasing. The observation is over here, when the particle's moving upward, the derivative of s with respect to t is positive. Over here, when the particle is moving downward, the object is going downward, then the derivative of s with respect to t is negative. Hey, these were velocities, right? So this would say the velocity is positive when the object is moving upward, and velocity is negative when the object is moving downward. And we could deal with this in terms of horizontal lines or any lines for that matter, but more easily visualized in terms of a vertical axis, I think. Think about throwing a rock up in the air and having it come down. Got to throw it straight up and have it come straight down. We don't have room for any horizontal and vertical motion. We've only got motion along a line with what we're modeling. You buy this, that the derivative is positive here. Yeah, derivative is slopes of tangent lines. And if I draw tangent lines to this curve, yeah, they're going to have positive slope. I draw tangent lines to this curve over here, they're going to have negative slopes. So when, in this setting, the derivative is positive, the velocity is positive, the object's moving upward. When the velocity is negative, the object's moving downward. We'll define speed to be the absolute value of velocity. So easy enough, the speed is the absolute value of v of t, absolute value of ds dt. Okay. There's a difference in speed and velocity. So now I'm working my way more into a physics type conversation. You may have heard it said that velocity is a vector quantity and speed is a scalar quantity. Velocity has magnitude and direction. Scalars don't, speed doesn't. Speed only has a magnitude. Notice, it's observed up here, the speed is non-negative, and it's the absolute value of something, so of course it's non-negative. In our setting, which deals with motion along a line, I didn't notice this term in the book, but it's called rectilinear motion. It's got to be somewhere in there. We indicate the direction of velocity or of acceleration by the presence of a positive sign or a negative sign. If we've got movement up and down, that is, if we've got movement of an object along a coordinate axis, which is vertical, as in the previous picture, then the positive sign will indicate on velocity that the object's moving in the positive direction, upward. A negative sign on velocity would indicate that the velocity is negative, the object is moving downward. If we had a horizontal axis, then the presence of a positive sign, say on velocity, would indicate movement in the positive direction. To the right, if we had a horizontal coordinate axis. Negative would indicate to the left. So we could just as well have an object moving back and forth along a horizontal line instead of up and down on a vertical line. Hey, the positives indicate the direction, and there's only two directions, the positive direction and the negative direction. So if you think of velocity as a vector quantity, that is having magnitude and direction, the direction's indicated by a plus sign or a minus sign, because we're stuck in one dimension. You get out there in two or higher dimensions and have a nice time, you'll have legitimate vector quantities there. And this will be dealt with in the calculus sequence in Calculus 3. But for us, one dimension and directions are indicated by plus signs or minus signs for us. So we are dealing with vectors in here, quite technically. They're one-dimensional vectors because we're dealing with motion along a line. All right, let's see. Speed is the magnitude of velocity. So there's a distinction between speed and velocity, even in one dimension. Let's look at a picture. Example 3.4.2 in the supplements. Let's go there. Okay, they give you this image. They say this figure shows the graph of the velocity v equals f prime of t of a particle moving along a horizontal line. Okay, so you would want to visualize a horizontal line with a particle moving back and forth along that horizontal line. Use this graph to describe the movement of the particle at various times. Okay, so this is a graph of the velocity. This blue curve here is the velocity function. Some quick observations before we analyze it in detail. Velocity is positive here. That is for time. This is a time axis. For time between 0 and 3, velocity is positive. At the endpoints, it's 0. For time between 3 and 5, velocity is negative because it's below the axis. It's 0 at the endpoints. Between 6 and 7, velocity is also positive. It's 0 at 6. So we've got positive velocity followed by negative velocity followed by, actually there's a little place where the velocity is 0 followed by positive velocity. Positive velocity along a horizontal line indicates movement to the right. So what you got is that particle moving to the right for this amount of time, stopping, velocity 0 at 3, moving to the left, velocity is negative, for time between 3 and 5 seconds, stopping, staying stationary from 5 to 6 seconds, and then taking on a positive velocity that is moving to the right again. So what we would see just in terms of forward, backwards, and stationary, you'd see the particle moving forward to the right, stopping, moving to the left, stopping, staying stationary, and then moving to the right again, based simply on the fact that the velocity is positive, and then negative, and then zero, and then positive. Okay, and that's roughly what's described here. When the velocity is positive, the particle's moving forward. Forward is to the right because we were dealing with a particle lying along a line. And that happens for t between 0 and 3. Yeah, here to here, we've got positive velocity, and 6 to 7 in the little blue bands that they've used here. When v is negative, the particle's moving backwards to the left along a horizontal line, and that happens for t between 3 and 5. T between 3 and 5 along here. On an interval for which v is 0, the particle's stationary, and that happens between 5 and 6. It took me a little shrinking of the image to get it to appear on the slide, but yeah, the velocity, the blue graph, is 0 between 5 and 6. So the particle's just sitting there with 0 velocity. Sitting where, I don't know. They didn't talk about position directly. They've talked about position indirectly. They've talked about velocity directly. I know between here and here, the velocity is 0. So between 5 and 6 seconds, the particle's just sitting there. Velocity is changing from positive to negative at t equals 3. Okay, so right here, we had positive velocity, then 0 velocity, and then negative velocity. What that means is the particle was moving to the right, and at time t equals 3, it stopped, and then it started moving to the left with negative velocity. Hey, similar kind of thing here at t equals 5. We had a negative velocity up to t equals 5, well, doing, say, 3 and 5. So what was happening was that particle is moving to the left. At t equals 5, it stops, and it sits there from time equals 5 to 6 seconds. And then starting at 6 seconds, it starts to move back to the right with a positive velocity at that stage. The velocity gets bigger, and it actually starts to move faster as time goes by, between time 6 and 7. More of that in a second. But that takes care of an explanation about the particle moving to the left and the right. Just simply based on where the velocity is positive, here and here, and where the velocity is negative, and even a little interval where the velocity is 0. Okay, let's see. When the velocity is increasing and positive, okay, increasing and positive, that happens here, then the object is speeding up. The velocity is getting greater. It's speeding up and moving to the right. Velocity is increasing and positive. That happens between here and here. Time between it should be 0 to 1. Time between 0 and 1, it's speeding up because the velocity is increasing, and the same kind of thing happens between 6 and 7. Yeah, sorry, typo there. It should read 0 to 1. We've got it, velocity increasing here and increasing here. So that represents a greater and greater velocity, and so a greater and greater speed. Okay. When the velocity is constant, the object has a constant speed. This happens between 1 and 2. Velocity is the same. It's moving at a constant velocity, whatever the v value is along here. They didn't calibrate the axis, the speed axis, the velocity axis, so I don't know what the velocity is, but it's constant. So it's moving at a constant rate from 1 to 2. And from 5 to 6, it's also moving at a constant rate. Well, that rate is 0 between 5 and 6. I do know the value of the velocity there. But we've got constant velocity between 1 and 2 and constant velocity between 5 and 6. For t between 3 and 4, here to here, the velocity is decreasing. Right? I mean, that velocity curve is going downward. So velocity is decreasing, but its magnitude's getting bigger. The absolute value of velocity is getting bigger. Remember, speed is absolute value of velocity. So what happens between here and here is the velocity decreases from 0 feet per second, they didn't give us units exactly, down to whatever we have here, but that's a larger in magnitude value. It's further from the axis, so in magnitude it's larger and represents a greater speed. So we have a lesser velocity and a greater speed. Yeah, we've got a velocity of 0 here and a speed of 0 here. Down here, we've got a lesser velocity, say negative, I don't know, 5 feet per second. Negative 5 is less than 0. So it has decreased, the velocity has decreased, but the speed would be the absolute value of that. And the speed might be 0 feet per second here and 5 feet per second here, the absolute value of negative 5 feet per second. So the object is actually sped up for time between t equals 3 and t equals 4, though the velocity has decreased, the speed has increased. What happens between 4 and 5? Now let's see, velocity is increasing up to 0, and the speed is decreasing. Absolute value of velocity is decreasing. Say the velocity is going from negative 5 feet per second up to 0 feet per second. Well, then the speed is going from 5 feet per second down to 0 feet per second. Velocity increases, yet speed decreases. Speed is absolute value of velocity. It's how far these points are from the axis. So you're measuring distances, which are never negative. The output values are negative down here. The velocity is negative down here. This is a decreasing velocity, yet an increasing speed. And that explains the speeds up, slows down comments that they've made in the picture. But that's the trickiest part of this to think about, is what's happening here where the velocity decreases and the speed increases, or where the velocity increases and the speed decreases. It's all based on the fact that the velocity carries with it here a negative sign. That's why we talked about these first. When velocity v decreases, and when velocity v is decreasing and positive, then the object is slowing down. So this happens for t between 2 and 3. Yeah, we've got a high velocity here down to a velocity of 0. So the object is slowing down on this interval. Between 4 and 5, it's also slowing down. As just discussed, the velocity is actually increasing here, but the distance of these points to the axis, that distance is the absolute value, it's the speed. The distance is getting smaller, and it approaches 0 over here. So big speed, minimum velocity, speed and velocity both 0 here, speed and velocity the same when things are positive. Only gets confusing when the object is moving in the negative direction, when its velocity is negative. Rate of change of velocity is called acceleration, as we'll shortly see. So when's the particle accelerating? It's accelerating when the velocity is increasing. So velocity is increasing here. It's constant there, it's decreasing there. Velocity is increasing here from 4 to 5. So 0 to 1, 4 to 5, and 6 to 7. So in those places, the velocity is increasing, so the particle is accelerating. Acceleration is positive. What about when velocity is decreasing, which happens from here to here, and then here to here, and that's it. So between 2 and 3 and 3 and 4, 2 to 3 and 3 and 4, velocity is decreasing, then the particle, the object, must be decelerating. So deceleration is decreasing velocity, acceleration is increasing velocity. You might argue I could include those endpoints. There's a comment about including endpoints. Right now, this will do for our conversation. When we analyze graphs of functions in terms of increasingness and decreasingness and derivatives, we'll elaborate on this a little bit more about what to do with the endpoints. For now, let's just leave the conversation as is and exclude the endpoints. You want to include them, go right ahead. I can't argue with that. When velocity is constant, and that happens between 1 and 2 and 5 and 6, then the acceleration must be 0. Velocity is not changing. Velocity is a constant on those intervals. Okay, let's see. We got another example to do shortly. Let's get some more definitions out in the open. Let's formally define acceleration. Acceleration is the derivative of velocity with respect to time. If a body's position at time t is given by s equals f of t, then the body's acceleration at time t is acceleration is the derivative of velocity with respect to time, or if you like, it's the second derivative of position with respect to time. Jerk possibly you haven't heard of this, is the derivative of acceleration with respect to time. So the jerk, J of t, is described to be the derivative of acceleration with respect to time. Well, acceleration, from the previous observation, is the second derivative of position, so jerk must be the third derivative of position. Why do they give it such an offensive name? Okay, let's talk very physical stuff that you have experience with. Newton says force equals mass times acceleration. You ain't accelerating, you ain't feeling a force. So if you're riding along in a car at a uniform velocity, constant velocity, then you don't feel any acceleration from the car. When the car speeds up and you depress the gas pedal, and you feel pushed back in the seat, you feel the acceleration. You slam on the brakes, you're thrown forward. You're accelerated because of the change in velocity. So how do you reflect a change in acceleration? One way to do it is by thinking about changing direction. Velocity has magnitude and direction, so we can change velocity by changing the magnitude, which depressing the gas pedal or hitting the brakes both do, or by changing directions. You take the steering wheel and just change the direction, you're changing the velocity, and so you're experiencing acceleration. You're also changing the acceleration when you change directions. So if I drive at a steady speed in circles, I feel like I'm thrown to the outer radius. If I'm turning to the right, I feel a little force that pulls me to the left. And that's a constant acceleration. I'm pulled to the left by a constant amount. But if I take the steering wheel and I swing it back and forth, then that car's going this way and that, and you're getting thrown left and right. You're feeling forces, but they change. That's what jerk is, and that's why they call it jerk. For us, I just need to know these differentiation definitions, but it gives a tangible physical meaning to a lot of this calculus stuff. So this is worth our while.